Okay, so we now have the conclusion, part 4, of chapter 15, where we're going to talk about the convolution integral and, of course, discuss how that relates to the Laplace transform. This is a very important integral for finding the time response of forcing functions with transfer functions. So let's get into that. So the convolution integral is an important part. We'll show how this ties together, but it's an important part of finding out how systems respond, and that's what we're going to be after here. So here is the convolution integral, two ways in which it's described. This is this first one here. This is this thing. This is really a definition, right? It just says over all lambda, so now lambda is a dummy variable, not not like time or that, just a substitution. But notice our original, what we're looking for is a function of time. So we've made a substitution here, and time is involved in this, but we're really dealing with something that you'll come to see as an offset. Kind of like this. If we have a system and it's described by some response, we call this the impulse response, some time response, and we force it with some input as a function of time. What we want to know is, what do we get in response? Okay? And sometimes this is called the forcing function. This is the impulse response, and this is the output. All right, these things, like not the forcing function, but the impulse response, is something we are often obligated to find. You can sort of get the sense even from the picture of transfer functions and the kinds of things we've been studying. So the convolution integral is going to help us determine our system, however we describe it here. If it's given a certain kind of input, what's the response going to be? So we're going to work toward that. Right away, there's some properties important, one of which is the impulse, not the impulse, the convolution integral. This starred thing is kind of a nice shorthand notation. You'll see it, and it's kind of reserved for that. It's commutative, right? We can put them, x can commute with, x can convolve with h, or h can convolve with x, and you get the same response, right? The time function, if I convolve the time function responses. So we're going to try to put some picture shape to this. If we go back and say, what are those convolutions? So in other words, putting it in terms of the definitions, right? Transferring this down and this down. These are what? These are the definitions at work. So all that's gone on there is translating the time to the dummy variable. And notice these limits of the integral are plus and minus infinity. All right, all of that is just definition type of thing. Maybe the picture, setting the framework for it. Here is what convolution is. They give a nice statement of it in the text, so I just copied it here. And take a look. There's a lot of important convolution of two signals. That's what we've got in the upper left in my little boxy thing. Consists of time reversing one of the signals, then shifting it, multiplying it, and doing that point by point with the second signal, and integrating the product. Okay? Four things going on there: time reversing, shifting, multiplying, and integrating. All right, so now let's assume that we have an x of t that's equal to 0 for t less than 0. In other words, we want to get rid of that whole bottom end of the integral, right? We've got this, just copied it from up above, and what do we really want to do here? We're just trying to adjust this, okay? And we can get there if we do that. Now, the second thing we'd like to say about all this, we can do this if x of t is that, but we've spent a lot of time saying that these are commutative and which one comes first. So it would really be pretty good if we say x of t is the forcing function and h of t is the system response. We'd like to know that h of t is something that we call causal. And causal means something causes something else. And if it's causal, so if it's causal, then what? H of t is equal to 0 for t less than 0. Right? Also, that would mean then it doesn't mean, but we want this to be true. It means that h of t minus lambda, it's kind of important here because is 0 for t minus lambda, for t minus lambda less than 0. In other words, what is this saying? If I shift the response in time, I want it to be equal to 0 as long as that time, the shifted time, is less than 0. Right? This is just saying if my shifted time is less than 0, right? That's what I really want. Then I want the function of shifted time to be 0. I don't want any monkey business going on when I start shifting the function in time. That's really all that's assuring me of. All right, a lot of definitions there, potentially a lot of work. Let's see. This is just, all of this gets pulled together with this, as he tends to do in the book. But now we've got things based around 0 and t for the limits. They're not just running away between infinities or 0 and infinities, okay? But we are still integrating with respect to the dummy variable. Okay, we're not integrating with this. T is now one of the limits. All right, what have we got? Properties of the convolution integral. They're just listed. We kind of named this one right away. Yes, commutivity. That just declares, one as the system, the impulse response, and the other one the forcing function. They're distributive. All right, so if I have an f of t, if I have three things going on, f of t, h of t, and y of t, I can distribute f of t over x and y, right? We like that. That's this nice summing property. It gets preserved. They're associative, so if I multiply f of t times this, I can associate these, or I can associate it this way. All right, just nice algebraic properties that we like to see. All right, what about these others now? F of t times delta t, right? Remember, delta t is, what is delta t? Delta t is this thing, right? And this just says if I move that around from time t, if I move it around to t minus lambda, I'm still going to get f of t. In other words, I'm going to be able to extract f of t simply by convolving it with the delta function. Okay, and you'll see that obviously as your illustration of what convolution is grows. Here it says I can move it around. That's all good. Here it says I can take the derivative of the delta function, and that just reveals the derivative of the time function. And once again, if I involve the unit step function as my convolved item, that's the same as, ooh, look what that does. It changes the limits. And it says I'm now looking at the bottom end if I convolve. And you'll see that with the few simple steps of how to do the convolutional integral. We really want to stay out of as much nasty math as we can, but kind of unavoidable coming up. Some of it is. Like in the last section with the inverse, we were able to take advantage of the tables, reduce things with partial fraction expansion, completing squares, and so forth. I want to do that, or do as much of that math simplifying as we can here. All right, but this is a chapter on Laplace. So how did we get off with this convolutional interval thing? All right. If we have, let's say we have f1 of s and an f2 of s. All right, we have these two. Those are Laplaces. All right, what have we got? Well, here's our convolutional interval as a function of f1 of t and f2 of t, and we fill all the numbers in and we write it out like this. Okay? Well, what we've got is this. If we take and form the Laplace of this, right? That's this. This whole thing is inside here, and this whole thing, right? We hope is the product of two Laplaces, and we'd like to prove this, right? So this is what's coming down. We'd like to take advantage if we convolve two items, if we convolve two functions and take the Laplace of it, is that the same as multiplying the Laplace functions? This is the claim. Let's prove it. All right, so here we have f1 of s, right? This is what? This is the definition. This is defined. Okay. Now, we're going to multiply f1 of s times f2 of s, and that would be this, right? We're taking this definition for f1 of s, and we're going to multiply it by f2 of s, right? So here comes this guy. Here comes our limits. Here comes our f1 of s. Here comes this whole bit, gets over here, right, as that. And f2 of s now moves across to there. We've just multiplied both sides. We multiplied this and this by f2 of s. Okay, but recall, this is time shifting here. This e to the minus s lambda, right? That's time shifting going on. So that business under there, f2 e to the minus sa, all right, that's time shifting going on. So I've isolated that, or rather the text did, isolated this and said, well, that's the Laplace of, well, what's happening? Ballpoint pen, I think I got sloppy there. All right, what's happening is I now have f2. I'm taking the Laplace of the function I think I'm good here. Whoa, having a little trouble with this pen. All right, so I'm taking f2 times the function. And that ends up a Laplace, right? That's a time-shifted Laplace. Okay, so this is time shift, and that becomes, I'm just filling out the details. This is written. This is the actual math. But oh, this math, I don't know why that keeps doing that now. This math right here is just back this whole thing, bunch of scribbling going on, is going to be this, right? Fs, this is going to be this guy. Fs, F2 of S, right? So that means in our next step, this is going to give us this, right? I substituted this whole thing. I just found out what F2 of S e to the minus S lambda is, plug it all together, set out the math, and say, oh, wait a minute, I got that going on up here. So that must be F2 of S, and that means I've got F1 of S, F2 of S, and here we are just writing out the integrals again, right? This whole thing is substituted in here. Right? And if I just keep mushing things together, I now have, this comes down, I'm moving this inside that integral, and that's what happened here. And I've got the integral of this, and I can do that, only now it's times dt, or to the, it's going to be the integral of dt, because I moved that inside. I'm just rearranging some things, right? And that just says the product of f1 of s times f2 of s is the Laplace of the convolution. So there's the relationship that we're looking for. The Laplace, this is convolution, and this side is just the product of Laplace, right? The product of some Laplaces. And that's equal to the Laplace of the convolution, right? So that's a relationship going on that we're going to like. All right, let me, it's important now to get into some examples. So, for example, let's say here's an h and an x, and we're going to want to find the y, right? So we have two things that we're comfortable making the Laplaces of, right? And let's do that. So the convolution of these two, we just decided or showed, was the inverse Laplace of the product, right? This was what we just showed. The product of two Laplace functions is the Laplace of the convolution, right? The product, let's go back and take a look. The product, down here in the corner, the product of the Laplace functions is the Laplace of the convolution. So if I go the other way, the convolution, the convolution, is the inverse Laplace of the product. Okay? And the product is what? Here's, this is this guy, and this is this guy. These are what? Laplace transforms. These are Laplace transforms. Okay, so now we want to do partial fraction expansion of this to get it into the next form. So let's do that before we show what's in the text. So what have we got? Hx is equal to 20 over s plus 2 times s plus 1, right? And we know, or we were told from partial fraction expansion, this should be a k1 over s plus 2 plus k2 over s plus 1. Okay, but now it's time to really do this. So the first thing was what? It said to multiply by isolate k1, right? So multiply by s2, and it says multiply the, right, s plus 2 times the hx, right? So that's going to be 20 over s plus 1, right, is going to be what? S plus 2 times this, that's k1 plus s plus 2 over s plus 1, k2. And now remember, then let s be equal to minus 2. Evaluate it at that point. Okay, and when we do that, this term goes to 0. This was k1. So we're left with then k1 is equal to 20 over minus 2 plus 1 is equal to minus 20. Okay, we can do the same thing for k2. Let's do that. We can say s plus 1 times the hx is equal to what? S plus 1 over s plus 2 times k1 plus k2. It gets isolated. And let s go to minus 1, take on minus 1. So that means this is 0, and k2 will be equal to 20 over, what have we got? I lost track of what I was doing. K2 then will be equal to the hx up here times s plus 1 will be 20 over, s plus 2. And at minus 1, we're going to, k2 will be equal to 20 over 1, which is 20. Okay, so we put it all together, and we will have k1 of minus 20. We'll have this. Here, let me just plop it in there. 20 over s plus 1, right? That was k2. Got to make sure we get these guys in the right place. All right, that's k2. So there's our 20 over s plus 1, right, in this thing. And it's the Laplace of 20 over s plus 1 minus 20 over s plus 2. Why am I not seeing my pen here? Here we go. So this is k2, and this was k1, right? And off we go. So the convolution is the same as the inverse Laplace of these two individual items. And of course, we like that. Now this is going to end up, I may have to get my eraser involved here and look at the pen options. I'll use my eraser and erase some of this under here, and you'll see it nicely that, right, once we know that this term very nicely becomes that term, and that very nice. We're good at inverse Laplace, right? Because we just got to look them up in a table. And so there they both are. Okay, so we evaluated the convolution by actually working with Laplace transforms. So there's the connection. Now let me do one other thing here. Evaluating the convolution integral. I just wanted to break these out as steps, and then I'm going to show you a visual example. convolution is a very visual thing, and I would encourage you to work as many examples. Look online for some videos. Sammy Kahn, K-A-H-N, and his academy has some if you haven't discovered him. But let's look at what's happening. There's 4 steps. You fold first. You take the mirror image of H, we'll call that the impulse response, about the ordinate axis. And just so there's no confusion, right? This will be lambda in this direction. This is the ordinate axis, right? If you give a plotting pair, an XY pair, there's always the abscissa and the ordinate. This is the ordinate axis here. The abscissa is out this way. Okay? So you fold it around that. In other words, whatever you had here, you're going to fold it over to here. And this is going to be the pivot point. All right, then you're going to displace it. So that means you're going to set it over here someplace. And you're going to displace whatever it is that's sitting over here. You're going to displace it by t, right? So that means you're going to be moving it. Now you're going to multiply the product of the two. So as you displace it, what's really going to happen is this folded impulse response is going to move toward the non-folded one, which is sitting over here someplace. Right? So this is H and this is X. I'll show you this in a moment with an illustration. And you're going to move it toward X, and they're eventually going to intersect. And until they do, there's no response. And then you're essentially integrating the intersection. For a given time t, you calculate the area under the product of the displaced H with X. And you're going to do that over all 0 to t. And you're going to calculate y. The result will be y. Okay? So let me try an illustration here. This is it. I got red and blue boxes. I keep it simple. This is a fairly standard illustration, by the way, but I've got it set up for you here. Now notice here's, if I can find myself here, here's the ordinate axis at 0, right? And I've displaced this one, so we're going to call this h of t. It's no big deal. This is x of t. I could have done it the other way, but they're color-coded just so you can see how they move. Now these are 1 by 1 boxes. Notice they're -5 to +5. They're 1 by 1 boxes. Nice so that the area is 1, and as they intersect, it's real easy to figure out what the area of intersection is. Okay? And I'm going to move h of t toward x of t. Now here they are right before they actually, they're just touching, but they have not intersected. So any attempt at y of t is still 0 here. We will plot y of t along this horizontal axis. All right, now they've started to intersect. Here comes y of t. And it's equal to 1/4. Why? Because a 1 by 1 box intersects, and I've just shown it a quarter of the way. Really, as it started to move in, the yellow area is the integration. Okay, this is the area of integration. So as it's moved in and they're over by a quarter, so all of this area corresponds to that point right there. As it has been moving, I've been creating points all along here. I've shown you the moment at which it's at a quarter. Okay. Next moment. It's at a half. So this area is this point. Right? You can see this moving on. Now they're 3/4 of the way overlapping. That created this point. right? Getting there created all the points in between. The integral has been a continuous thing, but because I've deliberately chosen squares of equal size, you're going to get a nice straight line. And when they're fully intersected, the area corresponds to that one point. Okay? Now they keep on going. And notice the red one is moving away. The impulse response is moving away. So this whole area is back down to what now? That point. It's 3/4. Move again, I'm down to a half. Move again, I'm down to a 1/4. So there's that point right there. Annoying, I know, but there's that point. And just as they disengage, I have an area of 0, and so I create the point of 0. Okay, so what's going on here is the convolution said the time response, this is y of t. If of the system that said if I have an impulse response that's square like this, and I convolve it with an input, or vice versa, I have an input that's square, and I convolve it with an impulse response that's square, I will get a triangular response. Okay, and you can do tons of math, and you will come back to the same thing. I love these visual approaches. You need to get familiar with this by doing problems and practicing. What you don't see here is the folded effect of h of t. If I'd taken the previous one where there was, maybe something like this, a time response, when I flip that, it's actually then looking like this. And I'm going to move that way. Okay, we'll get a chance to see this with very non-symmetrical functions, but it's a good start right here. This is the description. Now we'll work problems. So we'll do now 3 of the practice problems. And here are x1 and x2. So this looks a little like the example that, the illustration that I just gave, except x2 is more interesting. The nice thing about this, before we begin, is this has what? Area equals 1, so any fractions of it are easy to determine. And likewise with x2, the numbers will be pretty easy. So it wants a graphical interpretation first. Let's do that. We have that here like this. We'll do 1, 2, 3, -1, 2, 3. And we'll leave x2, right, and fold x1 over here. Okay, and x1, right, we're going to move this way. So rather than do all kinds of them, I'll do like I did in the illustration where I just pick some important points of engagement. Yeah. And the first one here is obviously at 0. We've got a big point right here. There's no intersection, right? The next one would be possibly when this is halfway, just to convince ourselves how that's going. So what have we got? We've got an area, we've got a magnitude of 1 times an area of 1/2. Okay, so that's going to put a point at 1/2. This is 1, this is 2. Okay, and then when they're fully engaged, the first step of that will have maybe this area here, and that's 1 times 1 obviously gives us 1. All right, now the next interesting one might be when this moves halfway over here. This is 1, this is 1.5, clearly. So now we have, what have we got? We've got a magnitude of 2, right? So this whole integrated area is what? It's 2 times 1/2 equals 1. And this integrated area in here is 1 times 1/2, which is 1/2. So the total area, which I guess we could have gotten by 2 and taking out that little quarter, but the total area then is 1.5, right? So where does that go? We've got a point here, we've got a point here, and now we're at the halfway point, so we have a point here. There's our, keep them clear. In the last location, the 1 by 1 box is over here, right? So I'll indicate all of that this way. And this 1 engages with that 2, right? The area subtended there is 2, and the area here is 1. So that total area now is 2 by 1 equals 2. So you're going to have a point right here. Okay, so if we connect these, and we know because we saw how they came about, we've got a straight line there. All right, now how about as this disengages? So let's come out. It's getting a little messy, but maybe another point of engagement would be halfway here. And now we're looking at this whole area. It gets nothing out of this, 0. And it gets 1/2 times 2, which is 1. So in other words, we get the other part of this. That means down here at point 1.5, I'm already way down here at 1. Right? I'm way down here at 1. And at the last point, where's it going to be? If this keeps going out, I'll be out here, and I will have no engagement, so my final point will be down here. In other words, I'll be dropping twice as fast. So there's the curve done from graphical convolution. Okay? So we could write the equations for that, probably not too hard, right? That looks like it's t. The function is t when t is greater than or equal to 0 and less than or equal to 2. Right? Yes. And then it's the function is what, minus, not minus t, but maybe minus 2t when t is greater than or equal to 2 and less than or equal to 3. So that doesn't sound right. When t is 2, we need to have, so this can't be right here. Okay? That can't be right. The function has to be offset. So we know the slope is going to be a minus 2. So it'll be something minus 2t. And it has to be 2 when t equals 2. So, and it has to be 0 when t equals 3. So 3 times 2 is 6. So this must be 6, apparently, for that arrangement. And then the function is 0 when t is greater than or equal to 3. Okay, or we could just say otherwise, something like that, because it's also when t is less than 3, it's less than 0. It's also 0. Okay, so we have that. Let's try to do it now in the S domain. Okay, we'll draw our lines around this and start again. We could see, by the way, what the author got. Oh yes, there's the picture. All right, so now in the S domain, let's just start. We get x1 of S, right? And this is going to be equal to, this is something that turns on, so it's a step function that turns on. And then one time later, we're going to take away the step function. And how do we delay that? With an e to the minus s, minus as, and a in this case is 1. Okay, so that's 1 over s times 1 minus e to the minus s. Okay, and x2, let's get that as s. Remember what we're heading for here is that the product of the S domain representations is equal to the Laplace of the convolution. So we'll get an S domain version of the convolution. Then all we have to do is go to our charts and go backwards from there. Okay, so the next one is in the S domain is it starts off calmly enough, and then it adds another one. So instead of subtracting here, it's going to add with an e to the minus s. I'll write it on the other side. But then it's all going to turn off, so it's got to be minus 2 over s. That's our size 2 u function. And e to the minus 2s is when that happens. Okay, so we'll pull all of this together and get 1 over s, right, times 1 minus e to the minus s minus 2, e to the minus 2s. Okay? So now, as I just said, if the product of these two in the S domain, x1 of s, x2 of s, is equal to the Laplace of the convolution, x1 convolved with x2 in the time domain. Okay? So we're going to do that and then take the inverse Laplace. So if I try to do this, we're going to get what? I'll just set it up, 1 over s squared. And I'm already sensing I like that because that looks like a slope function, right? We did that once before. Times all of this, let's see. I'm just going to take the pieces. So I took this 1 over s times this 1 over s. Now I'm going to take 1 times each of those. So that's 1 minus e to the minus s minus 2e to the minus 2s. Now I'm going to take e to the minus s times each of those. Right? So this will be minus. Let's see, I have something wrong. This got copied wrong. Plus. So that's plus and minus. Now e to the minus s. So minus e to the minus s. Minus, let's see, I got e to the minus s times this. The product is going to be minus e to the minus 2s. And then minus times a minus is a plus 2 e to the minus 3s. Whoa. All right. We'll be cleaning this up as we go here. So let's see. Let's see what we got. Where is my pen? Here we are. All right. So what does this give us? Let me first clean this up. So this is 1 over s squared times 1. And here I've got e to the minus s minus e to the minus s minus 2 e to the minus 2s e to the minus 2s. So this is going to be minus 3 e to the minus 2s. And finally plus 2 e to the minus 3s. Okay? So I'm already feeling good about this because I see 3 points in time identified. This is time 0, right? This is time 2, and this is time 3. And those are the key points in our graph. Something happens at 0, the slope changes again at 2, and it changes again at 3. Okay? So this is a slope function. Whoops, what is this here? This guy. This is a slope function, right? So this is t. And this happens at time 0, so it would be t u of t with a slope of 1. Okay? And we saw that right at time 0. Then at time 2, we get something that's minus 3t happening when? At time t minus 2. So that's out there at 2. And then we get another one, a plus 2t, happening at t minus 3. Right? So these would be our u of t's, right? And now if we think back to Bode plots, although I'm not tightening that connection, you can look at this. What do you have here? You have, if I look at this over time, I've got at my time 0, 1, 2, 3, 4, da da da. At time 0, this says start a slope that goes up and on and on. At time 2, start a slope that goes down at 3 times the rate, but it's already heading up at 1 time the rate, right? So that would be something here. Whoops, I'm sorry, right here. That starts down, whoa, starts down like this. And then at time 3, take one that heads up at a slope of 2 like this. Okay, so this is this one here is a 1-to-1 slope. All right, this is a 2-to-1, and this is 3-to-1. So what's happening? You follow this slope up until this point right here. Then you add these two, so you're going to be coming down. These will not be parallel lines, of course. You're coming down at a rate of 3 minus 1, so this is 2-to-1. And then you're going to flatten it with a 2-to-1 after that. Okay, so these summing ideas, even though this is not Bode plots, but you can see mathematically the relationship. Very similar to that, in that you break things up. That's the partial fraction expansion thing going on, all of that. Let's do another problem. Okay, so let's do this problem. Just graphically find this convolution. Okay, and this is a nice, the G here is a nice little box. So I'm going to flip that one around 0. And I'll just do it on this axis right here. Let's just say, here's that guy. We're going to move him that way. All right, so once again, let's find a couple of key points. Obviously, here's one when it begins. Here's one when it begins. What's going to be a next important one? Let's take it when it's fully engaged here. Now, we don't know where that's going to actually intersect. All right, so when this is fully engaged, this area equals 1. All right, so it's going to be that area times the values under the curve. So I'm going to plot this likewise here. And so what's going on between these 2 points? At the time 1, all right, project this right down here, the time 1, we know that we're going to intersect the curve right there because we just have an area multiplier of 1. All right? Once it passes that point, like if we get down here, we still have area equals 1. The intersecting area is still 1. So now we're just going to be following this curve as long as I stay beyond this point of full engagement. Okay, it's fractionally engaged up until that point, and then it's fully engaged after that. So this is going to be the shape after. The shape in front of it has got a head like this, right? So it's going to be the old 1 minus e to the minus t thing tracking here. It's going to want to climb up to a max value, and the max value is going to get truncated, right? So we're going to see this curve and this curve in a clean way. All right, and we're going to probably want to know where that point is. But what goes on in here? What's the equation describing it in here? Right, this is our 3 is our maximum value, we know that. But that basic shape is, if it wasn't 3, it could be n, it would be 1. So it's going to be 1 minus, this was e to the minus t, so 1 minus e to the minus t, right? And we're familiar with that, so that's our t greater than 0 and less than 1. Okay, that's the shape of that curve. It's the falling curve subtracted from a steady curve, and you can see that here we're moving a steady box of area 1 in, and a falling curve. Okay, what is the value at t equals 1? What is the value of this? Well, it's 3 times 1 minus e to the minus 1. Okay, but we could write this as 3 times e minus 1, right, times, in other words, I'm going to factor out the e to the minus 1, e to the minus 1. So that would be a hard value. All right, so now if we just write the form of it in the next phase of time, in other words, after time here, it would be 3 times e minus 1, e to the minus t. That's our starting value, okay, for the second half of the curve. And this will be t greater than or equal to 1. And you say, well, what happened to this e to the minus 1 here? Well, it evaluated at t equals 1. The curve doesn't exist below that. And beyond that, this then is just the starting point, right? So it's offset. Anywhere else back here, right, it's 0. And way out here, it's going to be 0. Okay. It looks like down in the corner that is the answer that he shows. Okay, so in 1514 here, we've got a nice circuit. So this looks sort of practical for us, doesn't it? And we've got a straightforward voltage divider network. We want to find the voltage across here as a function of this. And so all I'm going to say is V out over Vs, this part we can do quickly, is the S form of this. So 1 over 0.5 is 2 over S over the sum of these two, the resistance plus 2 over S. Okay? And if we go ahead and clean this up in the obvious way by multiplying top and bottom by S, we get 2 over S plus 2. So that's not too daunting. All right, and this in the time domain, right, is 2 e to the minus 2t. Okay. Now, we want to do convolution. So we're going to take h of t. We know our vs of t, so now we have h of t. We've got our vs of t. That little gambit was really to find our h of t. So our vs of t is given right there. It's 10 e to the minus t. Okay? So now let's do the output, v out, as a function of t. And we're going to say it's what? It's going to be the convolution. When we get the convolution, right, we're going to end up, and then so we're going to do this as a convolution here, and let's just write out the whole nasty integral. From 0 to t, we have h of t, right, 2 e to the minus 2 lambda, right, we're doing the dummy variable, times the supply, 10 e to the minus t minus lambda, right, d lambda. Okay, so this gets us to 20. Let's get the constants out of there. Between 0 and t of what? Let's multiply it all out. We've got e to the minus 2t, 2 lambda, times e to the minus t times e to the plus lambda, if we want to do all that. All right, so continuing, that's 20, 0 to t, and I'm just doing the math in the order, that just sort of falls to me. E to the minus t, e to the minus lambda, d, lambda, and I lost that here. Okay, so this is then, where are we? Let's go back here, equal to 20 e to the minus t times what? Times e to the minus, we've got e to the minus lambda. I want to be e to the minus lambda d lambda between 0 and t, but this is 20 e to the minus t. I'm not sure I wrote it any different. Times what now? The integral of e to the minus lambda d lambda is minus 1 e to the minus lambda evaluated between 0 and t. Okay, and that's, so now we're at 20 e to the minus t times 1. The upper limit is, the lower limit is 0. So a minus 1 becomes a plus 1, e to the minus 1, e to the minus 0, 0. So that's 1 minus, now the upper limit is plus, but it's minus sign sitting out there, e to the minus t. Okay, so what does this come down to? This comes down to then 20 times e to the minus t minus e to the minus 2t. All right, and this of course turns on at 0, right, because our function here was 0 back here. So this is e u of t. Okay, and indeed that's what they show. So we have that. And we'll leave it at that since they just asked for convolution. You can see we could also have done this, by the way. I can't really resist the connection here. We started looking in the S domain just to find a transfer function, right? And if we did this in the S domain, we could say that V out of S is equal to what? Vs. So in the S domain, the forcing function is what? 10 over S plus 1, right? This is Vs of S. times the transfer function, which is what? 2 over s plus 2. All right? And we know we can do fractional expansion and get this to be k1 over s plus 1 plus k2 over s plus 2. Right? Sometimes nice on these simple problems to do them a couple of ways. So I'm going to take a few moments and do that here. So to evaluate, we have 20 over s plus 1 times s plus 2. And if we multiply that by s plus 1, as it taught us, and set s equal to minus 1, this will be the constant k1. And if we do that, right, that cancels. 20 over 2 minus 1 is 1, so this will be 20. All right, I can do the same thing again over s plus 1, s plus 2, and multiply by s plus 2, and evaluate at s equals minus 2. Those cancel. That will be k2, and that will be what? Minus 2 plus 1 is minus 1, so this will be minus 20. All right? Then if we put it all together, we've got k1 is, so we've got 20 times a 1 over s plus 1. If I do the inverse Laplace, that is what? E to the minus t. And then I've got k2, so I've got minus 20. 1 over s plus 2 is e to the minus 2t. All right, and obviously with a minimal factoring, we've got e to the minus t minus e to the minus 2t. All right, and of course the step function, since it doesn't exist before that. So once again, looks good both ways, and things correlate. So I hope you can see now the ties, the back and forth between Laplace and convolution, and mathematically even some of the similarities and mathematical similarities to breaking down frequency plots a la Bode, and now transfer functions and so forth. So this will be it for chapter 5. We'll move on.